Hello, honors chemistry peeps. I hope you did well on the first little gas laws quiz that we had. We're going to go ahead and finish up the chapter here Friday, Monday. And we have to talk about gas laws and chemical reactions. So, of course, you're thinking, oh man, there must be everybody's favorite thing, Stoich. Absolutely. So maybe in Stoich you figure out the moles, and then from the moles you put it into the ideal gas law to solve for pressure or something. That's what you're going to have to do. It's not too bad. It is a great day today out here on my porch, so when you hear all the birds chirping, don't be gel. Don't be jelly. All right, so gas law is an equation. The volume, okay, if we're talking about volume, okay, that's going to be in liters. Or amount of gas, the moles. All right, and a chemical reaction can be calculated from the ideal gas law. It can be determined from mole to mole factors from a balanced equation and molar mass. Those of you that were on the Zoom would know that that is going to be measured in grams per mole. So again, you might get this from the problem, and you may have to calculate this, and then you divide the two and figure out what element it is based on the molar mass. All right? Always remember, you need to know the molar mass. Grams per mole. Stuff we've been talking about for a long time. All right, moving on. So let's take a look at the first problem that we get. Okay, what is the volume? Okay, so we got volume in liters of chlorine gas. All right, so this is a diatomic. So we got 35.45 times 2. I'm just doing my little math ahead of time so I know what's going on. This is 70.9 grams per mole. I got my pressure at 27. Oh man, what are you doing, Miss J? You can't add that. You gotta add 273. I don't use Celsius. That gives me a fighting 300 Kelvin. Nice. It's needed to completely react with 1.5 grams. Oh, so we got mass. How can we do this? Well, let's see. Do we have pressure, volume, moles? But we're reacting. Okay, so this is a little bit different. So this isn't straight up PV equals nRT, which, look, I have all the information I would need for PV equals nRT. But I'm starting with aluminum, which is a solid, and I'm trying to find chlorine, which is a gas. So we got to do a little bit of math, unfortunately. So let's go ahead and take a look at the moles of aluminum. So 1.50 grams aluminum is, let's figure out 1.5 grams. So I got 1 mole aluminum. All right, again, nothing here is going to be surprising. All we're doing is combining problem solving. My son just had to do that in second grade, combining, where you get through one sentence and somebody had 100 things, and then so he's like, oh, the answer is 100. Then there's two more sentences where you lost half of the half, so you're down to like 25 or something. All right, so we get 0.0556 mole aluminum. Okay. So that's great. So now we got the moles of aluminum calculated. All right, so in order to figure out how many moles we have of chlorine, right? So we got to figure out moles of chlorine. We're going to go ahead and take this. Okay, so I'm going to take this number, and I'm going to show you what to do with it, but I got to get rid of everything else on my page. I don't think I added another page. All right, so bear with me. All right, so the number I had was 0.0556 mole of aluminum. Now, I need to use my balanced equation to figure out how many moles of chlorine I have. So, of course, you remember, okay, well, I got 2 mole aluminum, and I have 3 mole of chlorine. So when I multiply those together, I get 0.0834 mole of chlorine. I now have the ability to solve this problem because I now have my N value. N equals that. So I'm going to take this and put it equals PV equals nRT. And once I do that, I'm solving for volume. That's nRT over P. I got my N to be 0.0834. I put mole on the top. I'm just worried about going to run out of room. Alright, now I have 0.0821. That's going to be liter atmospheres per mole Kelvin. Alright, and then I'm going to multiply by 300. Remember, this was 300 Kelvin. And I'm going to divide that by my pressure from the problem, which was very simply put 1.2 atm. And I'm going to get my volume to be, I'm going to put it right up top. Volume is, if I do all that math, 1.71 liters of chlorine. Alright, so it's really not that bad. All you're going to do is get the moles from the balanced equation, pop it back into the ideal gas law, woohoo, and then you're done and ready to move. Okay, moving on. I'm going to see if I can, this is going to be hellacious, but I'm going to see if I can fit this all on one slide without having to do what I did last time. Alright, volume. Oxygen gas. Alright, we know that that's going to be 32.0 grams, so we're going to do something with that maybe. 24. So I got 273 plus 273 is going to give me 301 Kelvin. I got my atmospheres and I have 28 grams. Alright, so I'm going to go very small here. I'm going to convert this 28.0 gram NH3, I'm going to convert that into moles. I know that it's 14.01 and 1.01 or something like that. 17.03 gram NH3. You can do the math. You know how to do it. 1 mole NH3. That's going to give me 1.64 mole NH3 ammonia. Alright, I'm trying to find my space if I can do this problem. Okay, so I think I can make it work. So I'm going to make it small here. So I'm going to take my moles, 1.64 mole ammonia. Then I'm going to take that, oh look, I got, here, let me switch colors. I got 4 mole ammonia. I have to go to oxygen. Let me switch colors again. I got to go to oxygen. Oxygen has 5. And math team that assembles 1.64 times 5 divided by 4, 2.05 mole oxygen. Okay, well, wonderful news. Besides the fact that my math was terrible up here, now I'm looking at this again. This should be 297 Kelvin. Math team let me down on that one. Alright, wonderful news is that we can now solve the problem. Again, we're solving for volume. Volume equals nRT over P. I have my moles, 2.05 mole. I get to use that same R value. We're not using that 8.31. 8.21, and that's going to be, you know what the units are on that. Liter atmospheres per mole Kelvin. I got my temperature to be 297, not 301. And I'm going to divide by my pressure, which is 0.950 atm. I think I'm going to fit it all on one page. I'm going to be so excited. Volume. Give me a second. Okay, get my handy dandy pocket calculator out. You got to carry a calculator everywhere you go. In addition, you got to carry a periodic table. Like I have wallet-sized ones I was going to give you all out at the end of the year. But, yeah, I don't know if I'm going to see you. I would like to. Hopefully May 18th. We'll see. 52.6 liters of O2. I'm going to box my answer because I'm a good student. All right, 52.6 liters. All right, of oxygen gas. That brings us up to this point. So the big question is, can you answer this question? I don't know if you can answer it, but you're gonna be able to do this. Now, this is pretty cool, right? Because look, STP. Those of you that like to attend my wonderful Zoom sessions are going to know that liters is going to be 22.4 liters. So it's at STP, which is great. So you don't really have to do too much, right? We can do this a couple different ways. So, what mass of iron will react? So, let me think. I think you've already done the problem like this, because it's at STP. 5.50 liter of oxygen. All right. So wait a minute. STP. Oh yes. 22.4 liters of oxygen. 1 mole oxygen. Okay. I'm seeing what you're doing, Mr. Haight. Well, now I got to use the mole to mole ratio. 3 mole oxygen, 4 mole iron times, let's get the mass of iron. 1 mole iron. Man, I like this problem a lot better than having to put it back into the PV equals nRT. Right? So I got 55.85 grams of iron, which is going to give me a fighting 18.3 grams Fe. I'm going to box my answer because I'm a good student, but I have to go back and I got to check. Did I get it right? I'm going to go with number 2. If you have discrepancies with number 2, please let me know. Okay, and the final part of chapter 11 is Dalton's law. We save the best for last. It's basically the total pressure is going to equal pressure of one plus the pressure of another plus the pressure of another. So we're going to have 3 different or 4 different pressures, whatever they are, and we add them up. Or maybe subtract one off to figure out the pressure of the missing gas. Pretty easy law. Don't really sweat this one. There are a couple different things that we'll talk about that are pretty interesting. The partial pressure of a gas is the pressure of each gas in a mixture, right? Making up the total. If the pressure is the pressure that the gas would exert if it was in itself by a container. So here we go. So here's my oxygen. Here it is. All right, here's my oxygen gas particles. So let's just say that that's exerting a pressure of 0.7 atm. Pressure of my oxygen. Now I add in some carbon dioxide. Well, that pressure is 0.3 atm. Let me add some in. All right, so I'm adding it in. All right, 0.3. And then, last but not least, I add some methane, which is everybody's favorite. Pressure of my methane is 1.2 atm. So I litter this thing with methane. Here it is. So all we're doing, if they're in there by themselves, they'd have those pressures. If not, we're going to add them all up, and we get a fighting 2.2 atm. All right. Okay, so here's what it is. Here's what I've been talking about. Dalton's law of partial pressure states that John Dalton, man, he's the man, huh? John Dalton, Dalton's postulates. Now we got more from Dalton. Depends on the total number of gas particles, not the types of particles, just total gas. So it doesn't matter what gas it is. Could be xenon, argon, methane, sulfur dioxide. It doesn't matter. Okay, neon, hydrogen, doesn't matter. Oxygen, whatever. Exerted by a gas mixture is the sum of the partial pressures of those gases. Just going to add them up, no matter how many we have. All right. So again, a little bit better drawing than what I just did, but if you take a look, all we're doing is, okay, well, here's helium by itself. Here's the argon, and we mix helium and argon, and we take the two separate ones, and we add it together. Oh my gosh, the sum of their two pressures. Now we have 6.0 ATM. Crazy. All right, now, I just was watching a show on this. There was some divers in a lake a frozen lake in Russia, and they all got the bends because they saw a bunch of underwater creatures that they didn't know what they were. But what is the bends? When a scuba diver is below the ocean surface, the increased pressure causes more nitrogen. Remember, 70, what do we got? Like almost, so 60, so remember, I think we were like 21% oxygen. I'm just giving it a roundabout number. 78% nitrogen gas in our body. All right, that's in our body, 78%. Let me write that a little bit neater. 78% of nitrogen is gaseous in our body at all times. So what happens is when you dive, that nitrogen gas starts to dissolve in the blood. If a diver comes up too fast, the dissolved nitrogen can form bubbles in the blood, a dangerous and painful condition called the bends. For deep descents, helium, which does not dissolve in the blood, is added to O2. So they basically are going to give you a lot more oxygen and try to remove that nitrogen if you go on deep descents. It can basically like burst your eyeballs out. It's kind of crazy. You could be bleeding from your eyes and your ears and so forth if you do get the bends. All right. So this is a tough question. So we have a scuba tank, all right, holds 800, has a pressure of 0.45 atmospheres, and helium at 855 millimeters of mercury. What's the total pressure? Okay, so basically, first of all, let's make sure that we convert each of these to the same unit, right? So 0.450 ATM. Just doing this to make it tricky on you, you know. They couldn't give you both of the same units. 1 ATM, 760 millimeters of mercury. So I'm going to get 342 millimeters of mercury of my oxygen. So let's see. Okay, that's of my oxygen. Plus I had the 855 of my helium. I'm going to add those two together. I'm going to get 1,197 millimeters of mercury. That's my final answer. I'm going to box it because I checked and I was a good. Alright, so for some dives, scuba divers use a mixture of nitrogen and oxygen gas, nitrox, with a pressure of 8 atmospheres. If the oxygen in a tank of nitrox has a partial pressure of 2190, what's the partial pressure of nitrogen? Okay, so again, oh man, look what they did here. So we got to convert that. 8.0 ATM. We're going to go ahead and multiply that by 760. We got 1 atmosphere. All right, so we go ahead and do that, and we're going to get 6,080 ATM is my total. So in order for me to get the nitrogen, I'm going to have to subtract what I had. Minus 2190. Alright, so that's going to get me a fighting 3890 millimeters of mercury. I'm going to box that. I'm going to check it. Woo! I got it right. Alright, so pretty cool. Alright, now the last thing, which is going to be really hard to understand, but actually, no, it's not going to be hard to understand, but unfortunately you don't have a lab to do it with, and that's in gas over water. So what happens is, in order to collect gas, which we have done this year, we've done it numerous times, even when we blew up the hydrogen and so forth. Remember we did that hydrogen and then you filmed every flame, and then one flame was more powerful and less powerful, whatever, based on how much hydrogen you bubbled in. Well, the other thing in there was the vapor pressure, was the vapor of water vapor. So every time that you collect gas over water, you have to take off, to figure out what pressure of gas you have to remove the pressure of the water. All right? And to do that, you basically look at the temperature of the water. The temp of water, and then that'll give you the vapor pressure of water. All right? I'm going to probably say, I'm going to go out on a limb. Probably not going to test you on this because, I mean, not directly. Not directly test. Directly? Alright, not directly test. Alright, but you'll have a Dalton's Law problem, but it won't be probably this gas problem. So let's take a look. Alright, so we have the decomposition of potassium chlorate. You all knew potassium chlorate. I didn't even have to tell you. Noah, I heard you say it out loud. It was awesome. Alright, produces oxygen gas and solid potassium chloride. If we have 124 mils of oxygen collected over water at 760 at 20 degrees, how many moles of oxygen are produced? So again, this is what I remember I told you. I said you had to know this number. Okay, so basically, why don't we just do this first and get it out of the way? 762 minus 18 millimeters of mercury. So we got to do that first before we do anything, right? Isn't that got to make sense? So we get 744, and that's going to be our p-value. But it's asking how many moles. Holy crap. So we have a p now. Yes, you're right. We're going to probably have... Let me go back. We're probably going to have to use PV. I didn't give myself enough room. Equals nRT. Okay. I think I can do that. So I'm solving for n. N equals PV over RT. My pressure... Now, don't get mad. I'm not going to use units. I know I would always use units. But this iPad is not forgiving. 0.124 liters. How did I get that? Oh, okay. So I had to do 0.124, and I had to, and that was mils, right? And then I had to convert that. Oh, wait a minute. Sorry. 124 milliliters divided by 1,000 will give me 0.124 liters. Remember, I have to match my R value. And my R value for this one, I got millimeters of mercury, so I'm going to use that 62.4 millimeters of mercury times liters per mole Kelvin. And, oh, of course, they couldn't give me this. I got to add 273. That gives me 293 Kelvin. All right, so 293. And when I do all that lovely stuff, and I'm good at, thank God it's only asking for moles. I don't have to go to grams, right? I'm going to get 0.00505 mole of oxygen. That's kind of looks like what I got. All right, so you get this, you subtract it off, and then you put it into PV equals nRT. Basically, all you're always trying to do is get one of the factors you're missing from the data in the problem. Do I think I'll go this far? I don't know. I don't know if I'll give you one of those problems that you have to do on one of my little multiple choice quick tests. But I definitely would do the reactions and the gas. All right, we'll use... All right, so remember I just said this. The air we breathe, 78% nitrogen, 21% oxygen. We got carbon dioxide, argon, water. We have more methane now. This is kind of crazy. So we're adding a little bit of methane as we speak. All right. Why? Well, there's not as much meat going on, so there's more animals on the planet producing more methane. Partial pressures of gas during breathing. That inspiration, expiration stuff. It's always going to be the same total. Isn't that crazy? It's always going to be the same total. Right, so inspired, expired. Oh, what happened here? Oh, we used this. We used it. Remember? Cellular respiration, all those steps that you learned last year. We use the oxygen in our body. All right, and then we're going to give off what we don't use as carbon dioxide. Okay, I'm done on my little here. All right. So, almost done here. In the lungs, O2 enters the blood while carbon dioxide is released. In tissues, O2 enters the cell while carbon dioxide is released. You saw this last year. All right, you saw this. All right, and it went over, and we did this subtraction and so forth. So you should know that tissues and your lungs and everything is going to take oxygen and give off oxide. All right, and last but not least, in the body, O2 flows into the tissues because the partial pressure of oxygen is higher in the blood than it is in the tissues. So this is not facilitated diffusion. It's going to be just simple diffusion. All right, carbon dioxide flows out because of higher pressure. So again, simple diffusion. It does not require energy. All right, have a happy Friday. That's all I'm going to do. I'm not going to have you do any practice problems or anything today. We'll do those next class. Have a great day.